Okay, so today's talk is about 1 + 1 = 2, and time permitting 2 + 2 = 4. It's actually about conformal field theory and Yang-Mills gauge theory. Some of you have heard me talk about those things before. But I kind of want to start out with a broader look at some of the things that make 2 dimensions special, and some of the things that make 4 dimensions special. And then try to reach out. Hopefully we can get some more ideas. There's a mix of people in this field. We have experts. We have Herbert Spohn here. We have people who've been in this field for a long time, as well as newcomers. And I'm going to try to just tell some stories. So first of all, why does it that 1 + 1 = 2? Well, that means if you have 2 codimension 1 linear spaces, generically they intersect into codimension 2 space, which means that 2 generic lines in the plane meet at a single point. And you can generalize this 2 lines meet at a point thing. It also, if you had 2 curvy lines, like graphs of a function, and one crosses the other, then their difference has to be 0 at some point. That's 2 cars on a one-dimensional street can't get past each other without being at the same location at some time. There's also what they call the Jordan curve theorem. If I give you any sort of loop in the plane, it disconnects the inside from the outside. And that implies things, for example, like if I give you a square with boundaries like this, that if there is a crossing, say like you do percolation, if I have a crossing from here, I can't have a crossing from here without it intersecting this at some point. Okay, so you have to have intersections like this. And, proving something like this, it's not that hard. If it's a smooth curve, then it's sort of, as time varies, instead of seeing 2 cars, occasionally, out of nowhere, you'll have a new pair of cars appear. And then when 2 cars, collide, they can crash into each other. But there will still be some parity issue that, it's kind of not hard to check, that you still are always going to have, if the cars get by each other somehow, they still there has to be some point where 2 cars are at the same place. Okay, so that's, anyway, stuff we all probably know. This is also, this 1 + 1 = 2 is important because it implies that this Dirichlet norm, the integral of the gradient of f all squared, is scale invariant. So if I replace this function f of x with like f of maybe a constant times x or something, I rescale this. Maybe I'll say x over c. So I'm like scaling out by a factor of c. What's that going to do? That's going to mean that sort of the domain of f gets stretched out by a factor of c in each direction. So there's c this way and c this way. So that's c to the 1, c to the 1, which, as we know is c to the 2. 1 + 1 = 2. And but then if we're squaring, the gradient goes down by a factor of c when we stretch out. So the gradient squared goes up by a factor of 1 over c squared. Okay. So this 1 + 1 = 2 is exactly what makes it so that this Gaussian free field, so that this Dirichlet energy doesn't change when I kind of rescale space. Okay, and more generally, if I take a conformal transformation, so instead of c x over c, I put here some phi of x, where phi is some conformal map. The same sort of thing will be true because a conformal map is just locally, just looks like a scaling or a translation. So essentially the same thing implies that you have some invariance. So it also, there's this object called the Gaussian free field, where you basically take an orthonormal basis with respect to this Dirichlet inner product, and then you sum an IID Gaussian time each element of that basis. So, some alpha I fi, where these are IID normal 0, 1, and these are basis for, well, I'll say, the Hilbert space with the Dirichlet energy, So integral gradient f squared norm. So, this is something we call the Gaussian free field. And you can kind of easily see, if you transform by phi, each one of these fi's is going to have the same Dirichlet energy. And so, what you get after you transform will also be an instance of the Gaussian free field. You can kind of see a similar effect if you take a grid. Let's say, hop over here and, if you take an n by n grid, and I choose an IID variable for every edge, then that gives me some random what we'd call a flow, a vector flow. I think of it, I assign it to each directed edge, and so if the sign is negative, I reverse the arrow. So I get each arrow, there's a positive flow going in the direction of that arrow. And so I take this Gaussian random flow, and I can there's this obvious L2 norm on flows where you just sum the squares of the sizes of all of the flows on the individual edges. And, and so if I just project orthogonally, I can take any flow and project it onto constant flows and flows that are curl-free and flows that are divergence-free. And what you kind of ask is, so what's the magnitude of the constant flow? Well, you can see that, if I ask what's the total net flow in the vertical direction, well, I have n squared normal random variables. Each individual edge is like n01, right? So if I have n squared of these normal random variables, then the variance overall is going to be n squared. So I'm going to have a general surplus of plus or minus n as square root of n squared in this direction. Okay, and roughly n in this direction on average. Which is so that's how when I orthogonally project onto the constant things, I will get some extra amount of flow going this direction, and the magnitude of that flow will be an amount that gives me a total amount of flow of n overall in this direction. Okay, which is the same amount of extra flow I would get, by the way, if I just took a line segment and added 1 unit of flow to a path. So the way we think of it is, when you do the Gaussian free field, the amount of excess flow, sort of in the homological directions going around this way or this way, is equivalent to what it'd be if I took a constant order number of extra paths like this. Okay, and so we kind of, it makes you think that maybe if there's some way of putting paths in this thing. There's also another fact is that if I do critical percolation on a large square, so I already mentioned here that we can't have both of these crossings, but you can also check that if I do a critical percolation on here, then you always have either one or the other. There'll always either be if you do like bond percolation on this, you color every edge, or you have a dual edge that sort of crosses it, goes from the center of a face to the center of a face. Either there will be a path with edges or sort of a path in dual edges. And also I want to mention that if you think about spanning trees, if I give you a uniform spanning tree, so some kind of random spanning tree of this box, then there's always, if I give you any 2 points, I can ask, what's the path that connects them? There will be one path that connects them. And if I give you a second tree and a second pair of points, I can ask, okay, how many times does the path between these 2 points and these 2 points intersect? So if I give you tree 1 and a pair of points, x, y, and I give you tree 2 and a pair of points, zw, you sort of have a way of comparing them because, say these are vertices and these are dual vertices. I can compare these trees by just asking, how many times does this branch cross this branch? Okay, and so, and sometimes what we do is, well, because we don't like to have so many degrees of freedom, this is like 2 trees and 4 numbers, you might say, let's just like fix one of these trees to be like a reference tree. Maybe like T2 is like the all horizontal edge tree. And take Z and W just to be boundary points on the tree. And then just take X to also be a boundary point. And then you only have one, say, Y to vary. Or maybe take 2 of these points on the boundary and then take 2 of these points like right next to each other. And so if you take 2 of these points on the boundary and 2 of these points right next to each other, then what you're going to get is a height, you'll get a number for every pair where I give you a vertex and a dual vertex. And so if you think you have a grid of squares, then I can ask, how many times does this, if the default tree here intersect this interesting tree from here, that'll be some number. Okay, and just because of this general fact that the line and the dual line have to intersect exactly one location, you get some sort of interesting number for this. And this is what they call the height function for the spanning tree. It's basically it's not defined on individual vertices, it's defined on pairs, an adjacent vertex and dual vertex. So you divide this into 4 little segments. You have a number for each segment. And it's telling you, if you take the tree from here and the dual tree from here, how many times do they intersect? Okay, so that's all lovely. I can give you even some pictures of these things. Let me go to, let's see, there's one. I'm going to close this. It's probably not needed. And I'll go to here. Yeah, so here's a picture of, hex, where if you color the hexagons, there's always either, when you color the whole thing, there's either going to be a blue crossing from left to right or a red crossing from top to here. There's a game where you play it, one player is trying to cross this way, the other player this way. If you do this bond percolation I mentioned, here's someone's picture online. And it shows these different clusters. And if you're at criticality, well, you sort of know that you have a 50-50 chance of a crossing from here to here, and a 50-50 chance of a dual crossing from here to here just by symmetry, because exactly one of the 2 things happens. So you know that if you're actually at p equals 5, there's sort of a non-trivial. The fact that I have a crossing in red from left to right is something that only happens half the time. Okay, and often in quantum field theory, gauge theory, all these things, a big part of the problem is finding what are the right events or observables whose probability doesn't just go to 0 or 1 as the mesh size gets finer, because you're wanting to get some non-trivial limit often as the mesh goes to 0. So this would say, whether you have a crossing from left to right is a good candidate for such a non-trivial limit. Okay, so now 2 plus 2 equals 4. So this tells us 2 generic planes in 4D meet at a single point. So how do I visualize that? Well, you can't really visualize 4D very easily, but you can visualize 3D moving in time. So a plane in 4D is like a line moving in 3D. So if I give you 2 generic lines in 3D with generic directions, at some point they're going to cross each other. You can just sort of visualize that. At some point they meet, and then that's the point in space-time where these two planes intersect. And there are analogs of that, like the mean value theorem. Like generally, if I had a pair of lines, if I allow their speeds to change or allow them to become curvy, still think of it as like if I have 2 loops, say, I can't get them apart without having there be some time at which they intersect. And I can say, even if I were allowed to create little tiny loops out of thin air and then join them with my big loop, I still would not be able to intersect to get 2 links apart. Okay, and so that's kind of a general kind of topological fact that's not too hard to prove. So it's kind of, the idea of the fact that people on a street can't get past each other in 1 dimension, 2 cars, 2 angry drivers. So 1 dimension, 1 plus 1 equals 2. It's about 2 angry drivers on a one-lane street who can't get past each other. And here it's about 2 angry, people with boats whose ropes are tangled in loops, and they can't get away from each other because their boats are stuck. Right? Either way, there's a certain frustration. So it also tells us that the Laplacian inner product, if I take the integral of the gradient, the Laplacian f dot Laplacian g, that's scale invariant. So just like, or just, you can think of the Laplacian f squared, say the norm part. That's, if I, scale out, then the Laplacian goes down by a factor of c squared, and there's c squared times c squared. But then the overall space I'm integrating over goes up by c to the fourth, so 2 plus 2 is 4. That makes this inner product. And this so-called bi-Laplacian Gaussian field will be scale invariant and also log correlated. If you restrict to any two-dimensional slice, you get the two-dimensional Gaussian free field. And it's also related to what we call the Gaussian free field on one forms. And the discrete Gaussian free field on a torus, if I imagine I go here and instead of taking two dimensions where I sort of take an independent Gaussian, imagine now I take an independent Gaussian for every plaquette, every square, a normal 0, 1 random variable, okay? And I just do that independently for every plaquette. So in 4 dimensions, there are like 4 choose 2 planar directions, right? X, Y, X, Z, X, W, so imagine you choose an independent normal random variable for each of these little guys. And so that's, you have, say, if you look at, say, the ones that are oriented in this direction, and, and I ask, so I have like n to the fourth of them, and then the amount of surplus I have is going to be about n squared, that I get from random fluctuations, which is about what I would get if I added an extra sheet crossing this. Okay, so in, there's this, there are a lot of models in 2D where, like the double dimer model where you get some random collection of loops and height changes by a constant as you jump across one of those loops, and they might converge to the Gaussian free field in the limit. And this is saying that, well, the amount of fluctuations for like the big loop paths you have going across that, that have an impact on the overall height change as you go around homology paths, you should expect maybe a constant order number of these guys. Okay? And this is saying, well, if you had some version of this story, we don't really have a great proof that these random surface models in 4 dimensions, where you have some, collection of something like a double dimer, you have some collection of loops, and then maybe some of them might be homologically non-trivial. But, if you did that, then you would sort of expect that the non-trivial guys, you'd maybe have a constant order number of those. Okay. So surfaces in 4 dimensions really play the role that these paths play in 2 dimensions. All right. Also, what's the analog of this story here with the top and the bottom here? How many of you know the 4-dimensional analog of this story already before I tell it? Okay, no, then I get to tell you something kind of beautiful and pretty today that none of you guys already know. This is not a deep mathematical result, but it's something that you guys will probably be happy to know. So if I, 1 plus 1 equals 2, 2 lines meet at a plane, but I can sort of thicken the 2 lines a little bit, and I get these 2 tubes meeting at a square. And I can imagine I draw these 2 lines here. And well, this is just sort of saying that there's this top to bottom in yellow and left to right in orange. Because I know this overall yellow in the tube and orange in the tube intersect. It kind of makes sense that if I just restrict to this box, there must be a yellow line from here to here. If I have a yellow from here to here and an orange from here to here, somewhere they must intersect, even if the lines are a little curvy and whatever. And so what you want to do is kind of imagine that now, instead of thickening a line, you have like your 2 planes. I don't know how to draw 2 non-intersecting 2 planes here, but these are 2 planes in 4 space. And I can imagine I sort of thicken each one a little bit. So, it's a plane cross 1 by 1, cross, 0, 1 squared or something. So now I have a bunch of, here I could think of, I have a whole bunch of 1 by 1 boxes. I have a stack here and a stack here, and they meet at 1 in the center. So here you can imagine that you have a whole 2-plane of these 4-dimensional boxes, and another whole 2-plane of these 4-dimensional boxes, and they meet at 1 4 by 4 box in the center. Okay? And so now all you have to do is think, and again, there'll be 2 planes in the middle of these guys, sort of like some orange plane in the middle, and some yellow plane in the middle of this kind of thickened thing. And then I just need sort of what's the analog of, let's say, like these 2 boundaries and these 2 boundaries. Well, so on in 4 dimensions, there are 4 boundary faces, or sorry, there are 8 boundary faces. So if I have 0, 1, cross 0, 1, cross 0, 1, cross 0, 1, then I can set, maybe if I want to get a face, I just pick one of these guys and I set it to either 0 or 1. So like this is one 3-dimensional face. I set this guy to 0. And so the things here in the xy plane, the 4 faces that I can sort of get to from the outside in this xy plane are the 4 faces where I set this guy to 0, this guy to 1, this guy to 0, or this guy to 1. So they're like 4 of the faces that correspond to fixing one of the ends of these 2 coordinates. And then in the other side, I'll have 4 faces that correspond to fixing one of these 2 coordinates. All right, so each of these friendly guys here can go to 0 or 1, 0 or 1. And yeah, so, all right, so what does that entail? All right, so, again, it sort of just takes a little bit of work to visualize this. This is the boundary of the 4 cube is like something that's homeomorphic to the 3 sphere. And yeah, so what does this 3 sphere look like? Well, I mean, it's 8 of these. Each of these faces is a 3-dimensional object. So it's 8 of these cubes stitched together in some way. Well, if you think about it, these 4 edges, these guys here are stitched together in the way that, like, if here it basically just looks like a square, right? I set one coordinate 0, 1 to 1. I have these 4 choices for faces where I set both coordinates 0, 1 equal to 1, both 1, or the other one equal to 1. And so so if you kind of think about it, these 4 guys, they kind of look like, it sort of looks like a stack of 4 cubes. If I just look at these 4 3 faces, it's like taking 4 cubes and they're connected around the other side. So it's sort of like a donut with the inside filled in. So it's like a torus, but you include the inside of the donut, like the square donut. So that's what is topologically the union of these 2. And these 2 things will be another donut. And the way it works here, so if you think about this donut with these 4 cubes, if I sort of unravel and just look at the boundary of the donut, that's like a 4 by 4 box, where this is like the long direction here where it's stretched out, and this is the direction where it sort of wraps around to give you the donut. On the other hand, if I think about what's happening in these other guys, this is also going to be a similar thing, except that it's the other coordinates that I change. So it's going to be like I have it'll be like another donut, but I have the long side in the other direction. And so I'm taking kind of these 2 donuts and sort of mating them together along their boundaries. And that's what gives me this 3 sphere. Did anyone know the name for this, by the way?
It's related to the Hopf vibration.
Hopf vibration, yeah, or the Kierkegaard splitting, I guess they call it sometimes. So anytime you, all right. So yeah, so anyway, this is this kind of nice fact. And so that means if I have a loop that sort of goes around this, and then I have another loop that kind of goes around this thing, and I try to sort of extend them to the inside, they're going to have to intersect at a point. Another way you could think about that is imagine that you're taking the outside of your box and you're sort of shrinking it and just letting it shrink. and seeing what happens. And so as you shrink, what you get is a movie living in the 3-sphere. And so that means these two loops in the 3-sphere, they're now moving around. And the whole point is that by the time you get to 0, it can't be the case that these loops have disentangled themselves. So basically you have two loops in the 3-sphere that are entangled. One goes this way and the other wraps around it. So they're entangled like this, and at no point can they break apart. Okay? So this whole business of that I mentioned over there with percolation, you can't have a crossing here and a crossing here, has a precise analog in 4 dimensions that you can really visualize if you understand knots. Okay, there's no way you can get these guys apart. All right. Oops, sorry. I should know this. Okay, so now we're all right. And there's also something. How many of you know about cellular spanning trees? Is that a thing that people? Not a single person here. Okay, that's all right. So there's an analog of these uniform spanning trees in 4 dimensions, where basically, what's a tree? A tree means you have a subset of your edges where you don't have any cycles. Right. Another way you can think about it is if you have edges, there's a boundary operator where you take the boundary of a directed edge, and it gives you like the the target endpoint minus the starting endpoint, or something. And this, and if you have a cycle, then that means if I take this edge plus this edge plus this edge plus this edge, that all has boundary 0. So it means it's a set of edges where the boundary operator has a kernel. And so if you don't want to have a kernel, then you just take a maximal set of edges so that the boundaries of these span the space of all things you can get as boundaries of edges. So we think of it as like a spanning set of edges whose boundaries span the set of possible things you can get as boundaries. So well, okay, so you can just do that in any dimension with plaquettes instead of edges. And so I talk about boundaries of a plaquette, and I ask, is there something in the I take a set of plaquettes where the plaquettes form the boundaries of the plaquettes form a spanning space, a basis of the set of all points I can get, things I can get this way. And so in particular, here, cycles are forbidden, and what's forbidden over here would be like a surface. An orientable surface would be forbidden. Or an orientable surface that uses the same face twice, that would be forbidden. And so you want to choose a random one of those guys. Now there's a little bit of subtlety that comes up when you do 4 dimensions. Maybe I can simply tell you, you're able to draw something like a Klein bottle where you kind of have a surface that's orientable, but then it comes around and then meets itself here in such a way that would make it non-orientable if you try to glue those last two things together. Which means that maybe there's a plaquette here where these come back and meet, and this plaquette, they can't meet. So this would actually still be a tree in this direction because there's no orientable surface. It's non-orientable. But the other weird thing is that if I wanted to, when I take the boundary of this guy, what I get is 2 copies of this loop here, not 1. Okay, so which means, in the usual uniform spanning tree, if I give you an edge in the tree and say, give me this edge as a boundary of some sum of edges in the tree, you just say, well, take this branch in the tree from up here, the path that goes from one to the other, and then the boundary of the sum of all those is the boundary of this. Where here, the boundary of this other collection of plaquettes, it might be like twice this guy. And so it means there might be some finite index lattice. So basically what they call a torsion group, so a group of things modulo the lattice, where maybe I only get half of the things or a quarter of the things or something in my surface. And that 2 or 4 is what we call the torsion group size. And so it ends up being natural not to choose a weighted tree, but to choose a tree weighted by the torsion group size squared. and just has to do with what happens when you do determinants. Somehow that torus group size is a determinant of some sort of thing. You know how it always is with lattices, like if you take a plaquette and if you have an integer map where the image only hits 1 in every 10 points instead of every point in the integer lattice, then the determinant has to be 10, right? Because the cube has to go to something of volume 10. So it's basically you're just taking that stretch, and it turns out that all these things are counted by determinants of the Laplacian, and so basically what's the nice thing is that these things are these random trees with this right weighting. They are an exactly solvable model related to the Gaussian free field in exactly the same way that uniform spanning tree is in 2 dimensions. Okay, so some people like these random trees because this is an exactly solvable model in 4D that we can sort of perfectly understand. In fact, I don't know, how many of you have ever seen one of these guys? Probably no one, right? So I actually drew one for you. This is 4 dimensions, so you're going to have to pay extra close attention. So what I'll do is I'll show it to you in 3 dimensions. So you'll see like a 3-dimensional slice, and you'll see all the plaquettes in that slice. They're showed like transparently, so you can sort of see through. This would be like a 4x4 box. This would be on a torus. And then I'll show like the edges. So think about it if I have, at first I show a slice. Imagine this is a 3-dimensional slice, and I'll show all the planes, the faces that are included there. And then I'll show this sort of something in between 2 slices, and you'll see a bunch of edges, and I'll color all the edges that would be in that. So it's sort of alternate between you're seeing the plaquettes and you're just seeing the edges and imagining that the plaquette is going in the time direction. Okay, so this is going to be terribly enlightening, I hope. So here we go. This is a uniform spanning tree on the torus. And this is the tree. This is just showing the complements of the faces. I'm just everything that's colored red here is not colored red here. So if you imagine here the red ones for each plaquette, there's like a dual cellular spanning tree that would go from the, have the same center but go in the other 2 coordinate directions. And so there's kind of a natural tree and dual tree pair. And I don't know, do you get anything from this picture? Maybe not really. It's vaguely space filling. There are a lot of plaquettes. You can kind of see that if you were to add any extra plaquettes somewhere, it would allow you to make an orientable surface. It's a little hard to get much out of that. But maybe it'll give you a little bit more if I do a 3D version of this. So in 3D, it turns out the 2 plaquette spanning trees are just dual to regular spanning trees. So what I did here is just took a uniform spanning tree rooted at the top and the bottom of a cube. You can just do Wilson's algorithm, run a loop erased random walk stock when you hit the bottom of the cube or you hit the top. Otherwise you reflect off the sides. And you get some sort of a nice, this is the tree, you take everything that hits the bottom, and that's some tree rooted at the bottom, and then you replace each one of those points with a cube, and you look at the faces around the boundary of the cube. So these faces, they're dual, that you see, they're all dual to an edge that would sort of go from a point in the tree to a point in the dual tree, or to a point in from the lower tree to the upper rooted tree. So there's a tree rooted at the bottom face, a tree rooted at the top face. And it sort of guaranteed that I would have sort of a nice surface connecting these 2 sides. Okay, so this is kind of one simple way to get a surface in 3D. And here, sort of 3D is very nice because 1 plus 2 is 3. And so these 2-dimensional derivative surface models are just exactly dual to the 1-dimensional spanning tree. You sort of don't need to learn a new thing. And in 3 dimensions, you think if I had like a spanning tree like this, and I take a dual face, that's like dual to an edge the tree goes through. If I were to sort of remove that edge, then what would happen is there would be some surface that went around this tree. That sort of, and then that's what you would get as surface. Or if I add a dual thing, there would be some dual surface that sort of goes around. So you can kind of see what's going on there. And if I, if I take the dual tree and if I put in some take some scissors and cut a piece of tree, you can sort of see I'm cutting out some chunk that has a boundary. And if I take like a grid, a whole grid versus of guys, and I cut this chunk, this chunk, this chunk, this chunk, then I'll get some surface that spans this whole boundary loop that's made up of those 4 little surfaces. And it's somehow some boundary of the set of stuff that goes through this loop. And that makes you think also that there's a very natural way to compare 2 loops in true trees. So I can just do this exact same thing here, but except instead of taking a pair of vertices, I can take a pair of loops. Loop here, and then I can ask, okay, what is the surface spanning this loop in tree 1? What is the surface spanning this loop in tree 2? How many times do they intersect? And that'll be some number, and maybe a constant order number if those are apart. And this is the exact analog of the height function in 1+1 dimensions for usual spanning trees. So there is a notion of height function. These are related to the Gaussian free field in many ways. So this is, by the way, the same thing on a 60 by 60 grid. You can see that we end up getting a nice tunnel. If you zoom in, you can see smaller versions where it's not exactly simply connected. But you get these interesting objects. Okay. All right. So now I'm a bit more than 30 minutes into the talk, and I haven't told you anything about my own research, right? I've told you a lot of nice, beautiful stories and ways of thinking of things. Maybe just make sure I've exhausted all of those before so I showed you this picture. Here's another picture of zooming in near one of these critical percolation clusters. There's a uniform spanning tree where you pick a pair of points and look at the path between them in the dual tree. This is a spanning tree rooted at the boundary of the plaquette. This is, by the way, this I just wanted to mention that I'm just advertised that there's this Simons collaboration that I guess I am the director of, and Yilin and Frederic, anyone else here? Yilin and Frederic are on this as well, and we're hoping people here in this audience will come to some of our events. We're going to be hosting several events a year, trying to connect probability to conformal field theory, and the pictures on our website, they're all things in dimension 2, but the stories we tell are often in dimension 4 as well. And so we have a big game of trying to take these amazing things that have worked in dimension 1+1, A, understand those better, conformal field theory, things like that, but then B, also see what we can do in dimension 4, what things we can push through. So I'm also teaching a course this spring for those of you who are at MIT or who want to come by or watch it, where we'll just try to explore all these connections more deeply. So here I'll just mention some of this work, homological percolation. These 3 authors and a bunch of others have really explored this homological percolation. And so, for example, the fact that PC, critical probability, is a half. In 2 dimensions, when you're picking edges, well, in 4 dimensions, the probability is a half if you're picking faces. And they have to think of what they mean by critical probability, because it's not clear what sort of the infinite face. They do something on a torus and talk about when you switch from having a homologically non-trivial cluster to not having one. And there's this like sharp threshold at p equals 1/2. So a lot of this is very recent. This is just published in 2024. But there's a whole bunch of exciting new work. And they do this, by the way, they're generalizing this to I plus I equals 2I. So you can do these cells in I-dimensional cells in a 2I-dimensional cellular complex. For me, I'm very happy to just not go any higher than 2 plus 2 equals 4, because there I can visualize these things in terms of interlocking strings, and the homology at all sort of feels more reasonable to me. But yeah, so they have a lot of pictures. This is their example of their homologically non-trivial cycle, and there, several papers. This is a citation list for one of these guys, where they go, and you'll see gauge theory, lattice gauge theory comes up in some of these guys, random cluster models. This is all kind of connected to the way people are thinking about gauge theories in higher dimensions. Same thing with this critical spanning trees, cellular spanning trees. There are a whole bunch of papers here. This is Duval, Clivons, Martin, really understanding these connections between Laplacians of determinants. And it's all kind of a simple story, but they do lots of different examples and variants of this. And this, has 46 citations. I could even click on that. A whole bunch of people using this for different purposes. This is, I guess more citations. And now, I'll get to some of the things that I've been thinking about. So Euclidean Yang-Mills gauge theory, basically, you want to imagine for every edge in your graph, you choose a matrix. And here there are 2 by 2 matrices. You can imagine in general, and here there are matrices from just sort of discrete groups, so I could write the numbers easily. This is the group of rotations, 90-degree rotations and reflections. And so you put one of these at every vertex, and you insist that if it's sort of a flow, so that like if you reverse the direction of the vertex, you replace it with its inverse. Okay, so this is the equivalent of just giving a flow, sort of a matrix-valued flow to your gratis. And you can imagine choosing this randomly by just independently assigning a matrix to every edge. Or you pick a direction, assign a matrix to that edge, and then assign its inverse to the other opposite direction. And you do that for every edge independently. So you can start by taking what we call Haar measures. So if it's, this is what I mean, you take an independent uniform measure on the group, which could be a continuum group like UN or ON, SUN. And then you weight by this exponential of b to the sum of the real parts of the plaquette traces. So for every matrix here, if you, well, what you find is the trace is the sum of the eigenvalues of the matrix. And the eigenvalues of one of these matrices in one of these compact Lie groups, they're always all on the unit circle. So the real part of the trace is going to be big if all the eigenvalues are close to 1. And it'll be small as possible if all the eigenvalues are close to -1. And so when you weight by e to the sum of the eigenvalues, you're just sort of pushing all of these guys closer to 1. So all of these eigenvalues, sort of like a random matrix model, you have all these eigenvalues and they have some repulsive force between them. You're just sort of putting a little gravity on them that sort of weights them all a little towards 1. Okay, and so that's his weighting. And then the question is, if you do that weighting, you can take a Wilson loop, like a big loop, and ask what's the expected product of the matrices around some big loop. Okay, and the problem is to construct and understand the basics of a continuum version of this in 4 dimensions. So lattice Yang-Mills, we assign random n by n matrix for some compact Lie group to each edge of a d-dimensional lattice. Yeah, okay. Right, so now it's very similar to the Ising model. So here I picture on the right the Ising model. Ising model, remember that you take a plus or minus 1 for every edge. And then you, the weight you give for every edge. So you assign numbers to vertices, and this edge you assign is an energy that makes these two things want to agree. So basically you want the product of these two matrices to be close to 1. So this is sort of the discrete spin models. You would have a matrix at every vertex, and you want the product of matrices to be on, or a matrix and its transpose or whatever to be close to 1. And here as well, here you want the product of matrix around a loop to be close to 1. So it's just the Ising model, except we're willing to generalize beyond one-dimensional matrices to n by n matrices, and we're willing to go one form level higher, so that the spins live on edges and the energy weights come from plaquettes. Okay, but otherwise, and this is what we have to do if we want to go from very interesting in 2 dimensions to something that's hopefully very interesting in 4 dimensions. Okay. And right, so we use this. I said you can take uniform measure. In the Ising model, we take uniform measure here with the weighting that makes neighboring spins want to align. Weighting makes products of matrices on the same edge want to be close to identity. As compared to here, matrices around the same plaquette want to multiply to the identity. Okay, so continuum implement of 2D Ising model is well understood. So this is Schramm, Smirnov, Chang Wonder, I guess Dubino, Kupon, there are at least 2 Fields medals that have mentioned the easing model recently. It's a very beautiful story, and it turns out that these loops in the scaling limits are very closely related to the Gaussian free field and the uniform spanning tree, these SLE curves. Somehow, everything is very closely tied together in 3 dimensions. So all the stories I mentioned, the percolation story, the uniform spanning tree story, the easing model story, they're all super intertwined. Okay, now everyone's dream, especially when you sit late at night thinking, oh, wouldn't it be cool if, their dream would be that at some point you had such a nice unified theory for 4 dimensions. Maybe there's some relationship between this percolation model in 4 dimensions and these spanning tree models in 4 dimensions and the scaling limit of the Yang-Mills model in 4 dimensions. That's, okay. I won't try to say anything too precise. You won't pin me down or tell me I'm crazy. But that's the sort of thing people would hope for. So you probably know the Klein Institute said they'd give $1 million to someone who constructs this continuum theorem here, not inflation adjusted. And we think of Yang-Mills as a statistical physics model. Like the easing model, we want to understand this limit. And maybe you can understand it even if you can't right away prove these things converge to it. So, in this 2-dimensional case, Schramm thought about easing interfaces, and he constructed SLE as this limit long before they were able to prove that these things were the limits of these curves. And Polyakov constructed Liouville quantum gravity surfaces before they could prove that random planar maps converge to them. So, the story here is that sometimes the discrete models are just inspiration for helping you think about how to build the right continuum model. And so maybe having all of these continuum models in 2 + 2 dimensions will give us some inspiration. I'm hoping you guys will help me out on this because we don't have quite enough inspiration to solve these problems yet. So I need some hints from people in this audience. Okay, so we want to assign a random matrix. We want some sort of scaling limit. So there are these other approaches. So one approach is this SPDE approach, which you may have heard of, people like Bjorn Bringman, Sky Cow, Martin Heyer, a whole bunch of names here, Chandra Chatterjee, Chevyrev, and many others who are really trying to say, let's construct continuum Yang-Mills theory by figuring out what sort of PDE, if it existed, would have this thing as its stationary distribution. And they start out by saying, okay, we know what the Gaussian field should look like. We know sort of what the theory should look like at small scales. It should look like just sort of a Gaussian field in each of the 3 coordinate directions. We have a sense of what the scaling limit should be. It's sort of like the natural Gaussian field that lives on. It's basically, in the discrete model, it's this story where I say, you take an independent normal random variable for every edge, and then you weight by the sum of all the plaquettes. The square of the sum of the variables around any plaquette. So you try to make the sum around every plaquette be close to 0. And this is sort of in the limit, if you imagine that you're at a very high temperature, so each of these is just sort of like a Lie algebra element instead of a Lie group element. And so then the small scale things are commutative, so you're just summing the squares of the things around every edge. Okay, and so there you get a nice Gaussian field that we understand perfectly. And in 4 dimensions, it's sort of the 1-dimensional thing that's related to this conformally invariant 0-dimensional thing, this bi-Laplacian field I was mentioning. So it's this very kind of natural Gaussian field. And so we know that what we want to do is construct something a little bit off-critical. The idea is, they say, well, let's start with this Gaussian free field on a torus, and then let's sort of modify it by running this SPDE and see if over the long term it converges to something. And they've had, some tremendous success on this in 2 dimensions, and in some impressive but limited success in 3 dimensions, meaning they can show like these PDEs are well-defined for a finite amount of time. They can't show that they're well-defined for an infinite amount of time and that it converges to a measure in the limit, but a very impressive start. And 4D seems to be out of reach with the tools that this group has, as far as I know. That's what they would tell me. You can think of other ways of starting with a Gaussian connection and modifying the field in some other way, make it correct at some scales. Yes. Oh, yes, I'm out of time. Okay, right. Yeah, somehow, yeah. Okay, so let me just, let's see, should I say any more here? Let me just say that, let me just advertise a few of our papers. So I should at least say something about our own work. I have these wonderful co-authors who've had all these papers. So, recently, we have a number of papers that really, on these discrete models, make rigorous the connection between these surfaces and passes. It tells you that if I want to know the Wilson loop expectation for a big loop, the expected product of the matrices is equivalent to the sum over all the surfaces that span the loop. It's, there's some like model of surfaces, and I ask you how the partition function changes when you introduce a big loop-shaped defect. Similar in 2 dimensions, where if I insert 2 points far away, I ask what's the cost of doing that? How does that scale with the points? Here you ask cost how to scale with the loops, and you try to show. So recent papers are showing in it for a greater range of parameters that this thing has an area law related to what they call quark confinement, that as you stretch out the loop, the expectation decays like e to the minus the area squared. And so we have, we have this that really helps you understand the Gaussian theory, and we have all of these things that are really, and if I had like several more lectures, we could go through some of these stories. But I think, I hope the purpose of this lecture is to sort of welcome people who don't know a lot of physics necessarily, but who want some cool problems to think about, and to see that, what they're trying to do in 2 + 2 = 4 dimensions is really not so different from what we've spent the last couple of decades doing in 1 + 1 = 2 dimensions. And it may be that we just get stuck because it's harder in higher dimensions, but I think there's probably more stuff that we can do. So I'm looking to you for ideas. That's it.